On behalf of Pat Falcone, it's my real pleasure to introduce today's joint DDST and PLS Colloquium speaker, Professor Boubacar Kanté. Dr. Kanté is an associate professor of electrical engineering and computer sciences at the University of California, Berkeley. He received his PhD in physics from Université Paris Sud in Orsay, France, and was subsequently a postdoctoral researcher at UC Berkeley from 2010 to 2013. He served as an assistant and associate professor of electrical and computer engineering and a Qualcomm faculty scholar at UC San Diego before joining UC Berkeley in 2019. Dr. Kanté's research group at Berkeley is focused on experimental and theoretical physics in the fields of nanophotonics, plasmonics, and metamaterials applicable to global energy and defense applications. In 2017, his discovery of the world's first topological laser based on the quantum Hall effect for light was selected as one of the top 10 discoveries in physics world. In today's presentation, Dr. Kanté will discuss some of his recent research in this field with a particular emphasis on the question of laser power scaling, or how to increase the power output of surface emitting lasers. And so this is a particular topic that's of interest to the laboratory with potential applications for high power lasers. So we're very glad to be hosting you today for this talk. Before we get started though, just a brief reminder on protocol. This is actually a hybrid meeting today. So for those of you who are joining us online, I'd like to encourage you to go ahead and enter any questions you might have at any time in the Q&A box. And at the end of at the conclusion of the presentation, we'll take questions from the room here for the people that are here present, and then we'll go through as many of the Q&A questions that we have online as we can, as we have time for. So with that, please join me in welcoming Dr. Kanté.
Yeah, thank you for the kind introduction, and it's a real pleasure and honor for me to give this colloquium. And thank you for having me, and a special thanks to Marius Millot for putting the event together. So I'm Boubacar Kanté from Berkeley ECS, and also faculty scientist at the Material Science Division at LBL. And today I would like to tell you, what an idea to come to Livermore and talk about lasers. So, but I would like to tell you about lasers you have not heard of before, probably. So topological lasers, and what I would say a 6-decade-old challenge that has been around forever. Now, how do you scale the surface of a surface-emitting laser while maintaining its single mode? Power will scale as the surface. We don't know how to do that. No one knows how to do that, and the problem has been around for a very long time. So I claim that I solved the problem. I will explain to you what the strategy is. So before going to the detail of the talk, let me just quickly, this is also an opportunity to meet many of you, quickly discuss research that my group has done during the last few years. So I will discuss this today, what I call a topological laser. It is basically an interface between two topologically distinct mirrors. And unlike most of the lasers we know, the exact shape of the interface is not really important. And more importantly, this laser is non-reciprocal, meaning that when light is emitted, it can't go back to the cavity. So this work actually was selected in 2017 as one of the top 10 discoveries in physics by Physics World. So we have also implemented singularities of open systems known as exceptional points. And these singularities are really great to do sensing. And usually they are implemented using parity time symmetry, basically distributing loss and gain following some type of symmetries. And we have shown that we can implement them using fully passive systems, and especially polaritonic systems that shrink the wavelength of light. So that make the polariton basically match the length scale of substances, biological substances. And we currently hold the world record for nanosensing of immunoassay sensing, basically. And we have improved the previous record by a factor of 267, so more than 2 orders of magnitude. So, we also demonstrated the first bound state in the continuum laser. We demonstrated, actually, and also hold the record for the thickness and efficiency of a lens. So this is a planar lens that is only 300 nanometer thick and that actually has an octave bandwidth from 600 nanometer to 1200 nanometer, and maintain an efficiency of 70% in the entire band. So it is the thinnest and most efficient lens that we know of. And here, I will explain this today. So we use these topological lasers and make lasers that can directly laze on an orbital angular momentum mode. And more interestingly, we can actually emit. OM is a basis that is unbounded. You can emit an OM as large as you want. And you can also multiplex those. So I will talk about that. So I will not talk about this. We demonstrated the first topological metasurface. So around topological singularities, you have a phase. And we found that actually that phase can be used to design an antenna array or a metasurface. And you can use that phase to make a surface that is sensitive to the chirality of light. So I will not talk about all of this topic. Today, what I will tell you about are topological lasers and a new laser that I call BerkSEL for Berkeley surface emitting lasers. So what is topology? So this is an orange and a donut. I think that's not a surprise for anyone. So they are topologically distinct. The orange has 0 hole and the donut has 1 hole. So the number of holes is called mathematically the Genius number. And to move from one to the other, you need to punch a hole, and punching a hole is called a topological transition. So it turns out that this simple geometrical idea actually has some profound consequences in condensed matter. So for example, if I take an insulator, it has no free electrons. It has a band gap, so we know of those. But imagine you take a 2D gas of electron and you magnetize it. So electrons will orbit at the cyclotron frequency. So effectively, there is no net transport of current in the bulk. Okay, so this is also an insulator. It's a different insulator. So this is called a quantum Hall insulator. It turns out that this will be like the donut, and the other insulator is like the orange. So I will not go to the details. There is a topological invariant that we can define that is called the Chern number, which is the total Berry flux in the Brillouin zone. So these two insulators are different. So if you interface them, so I told you that this was an insulator, this as well, but at the interface, electrons can't make the full closed orbit. They make what we call skipping orbits. And you see that there is a net transport of current at the interface. So this is an insulator in the bulk, but at the surface, it is a conductor. So there is a state at the edge that propagates in only one direction, and that is actually robust because it doesn't really care too much about the exact state of the interface. So the theoretical discovery of this phase of matter actually was awarded a Nobel Prize in 2016. And then one of the awardees actually was at UC San Diego before moving to Princeton, said that some of these ideas could be transferred to photonics. And he wrote a paper in 2018 explaining how that could be potentially done with photonic crystal. But one of the issues was that you need a magnetic field, and magnetic materials, there is almost no magnetism when you go to high frequencies. So he said it could be done maybe in the microwaves, maybe in the terahertz, but in optics it will probably not work. And the other point is that when you look at these systems, so basically this interface, it is an electron current flowing at an interface. Optically, it will be a waveguide. Okay, so people have done a lot of work to try to demonstrate topological waveguides for light. So I was at UCSD, and then one of the questions that I asked myself was whether we could do more than just a waveguide. I'm not sure we need a new waveguide for optics. So even when you do the quantum communication in the future, we are still hoping to use the fiber infrastructure that is already existing. We are not going to replace all of the waveguides by topological waveguides. So the idea was simple. The idea was that if I take a topological interface that I have shown previously for electrons, but I will tell you in a minute how we can do that for light, and I close the contour, an arbitrary closed contour between two topologically distinct mirrors is what I call a topological cavity. And a few things, the topological cavity, of course, is one way because light cannot only go in one direction, not in both. I am in the room, you see me, I see you. It's because the medium between us is reciprocal. So if it was not reciprocal, light will go, I will see you, or the opposite. We will not both see each other. So here, light goes only in one direction. And I will have to explain what I call topological mirror. So what is a mirror? The mirror is basically the insulator for light. An insulator in electronic, the equivalent for light is a mirror. So And because this cavity, this arbitrary closed contour is topological, the exact shape of the cavity is not important. So if I were to make a laser out of this cavity, so this laser, this one and this one will have the same properties. So this is strange. You know, all the cavities we know are very sensitive to the shape. So this one will not be very sensitive to the shape. So the question is, how do we design these mirrors? So what we have proposed is to construct the mirror by bonding a free 5 semiconductor in green here on a magnetic substrate, like a garnet-based material. And on the platform, on the free 5 semiconductor, I pattern a photonic crystal with a band gap. The band gap is a mirror. And I have to design the band gap so that one of the band gap is basically the orange, and the other band gap is the donut. So this band gap is the orange, so it has a Chern number that is 0, the total B reflex again in the Brillouin zone, and I designed another structure that has a band gap as well, that is narrow, and this band gap is non-trivial. It is basically the orange. So if I interface these two mirrors, I will have an edge state at the interface. So this is what you see here. Here is one of the photonic crystal. It's a periodic structure. Okay, and then here is the second photonic crystal. They are distinct. One is the donut, the other one is the orange. And in the presence of the magnetic field, let's say pointing up, you see that light at the interface propagates forward. And if you flip the magnetic field, forward propagation is now forbidden, and light has to propagate backward. So this proves our idea that, in fact, we can indeed implement this edge state at optical frequencies using the platform that was proposed. And what is the cavity? The cavity is just an arbitrary closed contour of this interface. And here is an example of cavity. So if you have not noticed, we try to implement the shape of the US, and we flip it. So we put Canada on the south and Mexico in the north. So the claim is that this interface here is a cavity. Light will sneak around the contour because, again, the center guy is a donut and the other one is an orange. So they are both mirrors, but these two mirrors have different topology. Because of that, light can only go in one direction at the interface. And to prove that light is indeed going only in one direction, we couple the cavity to a waveguide. So what will happen is that when the magnetic field is pointing, let's say, up, for counterclockwise propagation of light in the cavity, so you will collect light on the right output of the waveguide, and you can flip the magnetic field, and light will now couple to the left output of the waveguide. You basically made a switch. You control light on chip with an external magnetic field. Exciting proposal. How does it work? So here is the experiment. So we fabricated the device. So you see the two photonic crystals here. And again, the photonic crystal is patterned on a free 5 semiconductor. And we pump the entire system optically with no magnetic field. When there is no magnetic field, we mostly see spontaneous emission out of the surface. And then why is that? Because with no magnetic field, the band gap of the non-trivial photonic crystal, the donut, is basically closed because that band gap is narrow. So if there is no band gap at the center, there is no mirror at the center. And if there is no mirror, there is no cavity. And we turn on the magnetic field. That opens the non-trivial band gap. The trivial band gap is always there because it is large. You can't close it with the magnetic field. So now we open the gap of the non-trivial photonic crystal, and you see this edge state appears at the boundary under optical pumping. And we show indeed that light is non-reciprocally emitted from the cavity, and we measure an isolation ratio of about 10 dB between the right output and the left output of the waveguide. And indeed, light can be switched from one of the output to the other just by switching the external magnetic field. So this was exciting. This was the first ever demonstration of a topological laser. And we continued to prove that indeed it is robust. We made cavities of other shapes. I haven't seen any cavity of this shape before. You see that regardless of the shape, you get lasing at the same wavelength with about the same isolation ratio. So this was really exciting. I think it was very surprising for the community as well because no one expected what I call it the photonic quantum Hall effect to work at such high frequencies. So after this demonstration, we asked ourselves if there was anything else very unique that we can do based on this platform. And this is what I will explain now. We can make laser that will directly laze on an orbital angular momentum mode. And that work was published in Nature Physics last year and actually made the cover of the journal in June. So the idea is also very simple. So I just told you that these edge states, okay, between two topologically distinct mirrors exist and they don't really care exactly about the shape of the interface. But let's assume that the interface is circular. And let's also design the edge state so that it sits above the light cone. So that means that as this wave propagates around the cavity, at each point, as it travels around, it will leak some of its energy out because it is above the light cone. But of course, there is a phase offset between light at this point and at a point x plus dx. So the phase difference is exactly the propagation phase between point 1 and point 2. So this phase difference naturally leads to the formation of an orbital angular momentum beam in the far field. And the interesting thing about this platform is that since the number of wavelengths around the ring can be controlled just by the diameter of the ring, I can actually emit in the far field an OM as large as I want. Because the OM, the topological charge of the beam in the far field, is nothing but the number of wavelengths that are guided around the surface. The OM, again, for orbital angular momentum, is a degree of freedom of photons that is completely different from frequency or polarization. So it can be used, for example, to do multiplexing of information because this is a basis of orthogonal elements. So, and more excitingly, if you look at the platform, it is just, again, the donut and the orange, two distinct mirrors that lead to the propagation of light in the ring. And the propagation is unidirectional. This is why I can get an OEM, because in a conventional ring, light goes in the two directions at the same time, and the net OEM is 0. So here I have an OEM that I can make as large as I want, and I can multiplex many OEM sources or lasers on the same interface. I just put the donut, the orange, and I alternate the donut, the orange, the donut. You can do that as many times as you want. So it just depends on how patient your students are. So we made 3 of them, 3 cavities here, and each interface is a laser, and they are multiplexed, and these beams are spatially orthogonal. So you could, for example, use it to communicate with beam 1, beam 2, beam 3 separately. You can increase the capacity of your communication channel using this type of beams. And many other things can be done with these OM beams as well. So we did the experiment. So this is theory. We demonstrated emission of an OM up to 276. I think this is the largest OM ever emitted by laser directly. Usually to generate an OM, you take a beam, a Gaussian beam, and you go for a phase plate. And usually, the phase plate gives you an OM of 1 or 2. If you want large OMs, the resolution needed in fabrication is become more and more challenging. So here, for the same resolution, I can emit arbitrarily large orbital angular momenta. So we have measured the characteristic of these OM lasers. So via laser, we also measure the G2 and clearly observe this suppression of the anti-bunching peak. That clearly shows that we have indeed a coherent light source. So this is exciting. So there are lots of things that can be done with these topological lasers. And we are still working on the platform. So here are some experiments on this laser where we take the beam and interfere it with itself. And the number of fringes that we observe here in the far field is nothing but 2 times the topological charge. So this is a proof that the beam emitted from these topological rings are indeed OM beams. Okay, so that was topological lasers. I want to tell you more about the main claim today, the Berkeley surface emitting laser. And here is an example of surface emitting laser that use a fancy cavity that we call bound state in the continuum. So I will not go to details today, but I just want you to notice one thing. For this bound state in the continuum, and for most surface emitting laser that you know, there is an aperture, and the aperture, the fundamental mode is a Gaussian beam, a Gaussian mode, with the field concentrated at the center and the field decaying to 0 at the boundary of the cavity. Okay? So this is the normal mode in any potential well. So, and we have shown in this paper, again, I'm not going to discuss this detail, but we have shown that these bound states in the continuum were favorable if you wanted to make compact surface emitting lasers that are small and efficient. But the motivation is exactly the opposite today. I would like to make this aperture as large as possible. And this has been a challenge. So it has been a challenge since the invention of lasers. So this is the paper by Charles Towns, who actually was a faculty at UC Berkeley physics for over 50 years. And he got the Nobel Prize for the invention of lasers. And from the very first paper, you can see here that they were indicating that a single mode may be selected. So it's not guaranteed. So it has been a problem since the invention of lasers. How do you make a single aperture, single mode at all scales? So today, to scale up power, the strategy is mostly to use fibers, right? So, and we amplify along the propagation of the fiber. So this is the state of the art, and you can make very high power with this type of strategy. So this has progressed a lot, benefited from progress in fibers that were developed for telecom. But if you look at the competing strategy, that is also interesting because here power rescale as the square of the linear dimension. So this is why people really want this type of solutions. And it will also be much more compact. It will be lighter if such a strategy could be pushed forward. So the state of the art currently is held by a researcher in Japan who can make photonic crystal emit few watts. But there are fundamental problems because, as I said before, sorry, the pointer is going directly. So the fundamental mode is, the fundamental mode is a Gaussian mode. And whatever you do, this mode always sits at the center. And the second order mode mostly sits at the boundary. So this is why it doesn't work. Because you can do a lot of engineering to try to push these two modes apart. But because they do not overlap spatially, there is always a lot of gain around the circumference for the second mode to laze. So no one knows what to do. So it seems to be against physics because those are the fundamental solutions of a potential well. Okay, if you do quantum well, it's the same thing. You get exactly these oscillatory wave functions. And it seems like we can't really do much. So if you look at the quantity that is usually used to characterize this mode, we call it the threshold gain difference. Basically, the difference between the threshold of the first mode and the threshold of the second mode. Of course, as the size increases, the two modes become very good. And this threshold gain difference, the threshold gain difference goes to 0. Meaning that at large size, you can't differentiate the first and second mode. They will laze. There is nothing you can do. So people have done some engineering. For example, the group I just told you about. So by making two-layer photonic crystal to try to push these two modes further apart, they have managed to increase power. But physics says that you can't really do more. Okay, there is a problem. So of course, this is single mode operation. This is multi-mode operation, and we would like to have this type of operation at all scales. So here is our idea. Usually, photonic system have, or electronic system have a quadratic dispersion at the band edge. And because of that, it fixes some distance between consecutive modes. And also because of that, the Q factor of all modes becomes very, very high. You see all the peaks are narrow as the size increases. The cavity becomes very good for all modes. So what I propose, and I will go to the detail in a minute, I propose to move from a quadratic dispersion to a linear dispersion, and also make higher order mode in the cavity more lossy. So how do we do that? So here is the idea. So if you take a photonic system, as I said, or an electronic, usually they have a quadratic dispersion at the band edge. So to make a cavity is a system of finite size. Let's say the size of the aperture is d. So the first mode will be at pi over d, the second mode at 2 pi over d, third mode, etc., etc. So the distance in frequency between the first two modes is delta omega 2, 2 for quadratic. So this distance, you can easily calculate it, is scaled as 1 over d squared, where d is the size of the aperture, meaning that as D increases, the distance between the fundamental mode and the second mode goes to 0. 1 over D squared, D increases, it goes to 0. This is the fundamental problem. If I make the dispersion linear, you can directly see from the image that the distance between the first and the second mode has increased. Delta omega 1, 1 for linear and 2 for quadratic. And now instead of scaling as 1 over D squared, the distance between modes now scale as 1 over D. So by moving to a linear dispersion system, I have increased the separation between modes in my cavity. So what is linear dispersion? It is basically the graphene for photons. So graphene has linear dispersion for electrons. If you make graphene for photons, you will have linear dispersion for photons as well. So you see here that, oh, actually I have increased the mode spacing, then it should be fine, but not really. That's not enough. Because even if 1 over D is larger than 1 over D squared, 1 over D also goes to 0 with the size. So it seems like I didn't solve the problem yet. Okay. So how do we form linear dispersion? So we need some group theory, but there are many ways to do it. For example, you can use a dipolar mode that you overlap with quadrupolar modes. And that works in infinite crystals, but it will not work if you want to do a linear dispersion in a finite size system, because a dipole will always be radiative in the presence of loss. And when you truncate a system to form a cavity, you will always have loss. So what we propose is that we need to implement linear dispersion using modes that are symmetry protected. Let's say the B1 mode here, that is non-radiative, and the E2 mode here, that is also non-radiative. So if you do that, you can implement linear dispersion, and here is an example. So we implemented a photonic crystal, infinite structure. So this is the dispersion of the infinite structure. You see that the dispersion is linear at the bound edge, and you have a point where the cone meets. This point is called a Dirac cone. And in order to make it a cavity, you have to truncate that system into a finite size. So it is truncated here to form an hexagon, and it is an hexagonal unit cell in the structure. And I want to give you an intuitive picture of why this system can be scaled forever. So if you take a constant omega, that's called an isofrequency contour. An isofrequency contour will cut the cone and form a circle. Okay? So when the isofrequency contour cuts the cone exactly at the tip of the cone, at the Dirac point, the radius of the circle is 0. So, and the radius of the circle is the effective index of the aperture. So that means that every point on the aperture is exactly at the same phase, because the phase is the index multiplied by the distance. So I take a point on the aperture here, and another point here, they are in phase at the Dirac point. So I have locked all unit cell, all resonators in the aperture in phase. And if you do that, the fundamental cavity mode in this, I call it an open Dirac potential, is not a Gaussian mode anymore. The fundamental mode is a flat envelope mode that occupies the entire aperture. So every unit cell here in the aperture participates in the lasing mode. I hope you realize we solved the problem. The mode is not oscillatory anymore. The field is not going to 0 at the edge. So there is no space for higher order mode to come into the picture. So let's look at the scaling of this cavity a little bit more. So the horizontal line here is the fundamental mode, and we calculated, yes? Yeah, indeed. Absolutely. So I will show you experiments. So yes, it is sensitive. I will go to that in a minute. So the question is, how sensitive is it to fabrication? Of course, it is a photonic crystal. So if you want to implement what I call an open Dirac potential exactly, so you need to have holes of the same size across the aperture, because if the size varies, you change the potential. Okay, so I mean, with current nanofabrication technology, we can really scale the aperture pretty easily. I will show you some experimental results on this idea. So the line that is almost horizontal is the fundamental mode. And then you see that in this, so the red, this is quadratic. This is quadratic. The radius is larger than the radius of the Dirac singularity. The radius is the radius of holes in the photonic crystal. And you see that when the size increases, or the surface increases, the fundamental mode and the second higher order mode come arbitrarily close when the dispersion is quadratic. And they come also arbitrarily close here when the dispersion is quadratic again. But here, they also come close, but as I said, instead of scaling as 1 over d, this distance will now scale as 1 over d squared. I say that is not enough, so the real, I call it real free spectral range, goes to 0 for both quadratic and linear dispersion. So when the dispersion is linear, this convergence of the mode is slowed down, but it is not enough. But now, if you look at the quality factor, which is the imaginary part of the free spectral range, sometimes we forget that the free spectral range is a complex number because the eigenmode is complex. The system is open. So the distance between the real modes becomes arbitrarily close. But if I can keep the distance between the imaginary part of the mode constant, the free spectral range will never vanish. So here, when the dispersion is quadratic, we show that the free spectral range actually goes to 0. You see the second mode come also arbitrarily close to the first mode. All modes have a quality factor that goes up with the size. But when the dispersion is linear, implemented with symmetry protected mode, the second mode never catches up with the first mode. And we prove that in the limit of infinite size, these distances go to a constant that is governed by the loss rate of the B and E mode I told you about earlier. So this is summarized on the slide here. When the dispersion is quadratic, the real free spectral range, or normalized, goes to 0 as 1 over d squared, or the wave vector square. When it is linear, it's slightly better, but it still goes to 0. But the imaginary part, the imaginary free spectral range, goes to 0 only when the dispersion is quadratic. And this is what is known. All known cavities have an imaginary free spectral range going to 0. Now, in the new cavity that I just proposed, this quantity here will stay constant forever, regardless of the size. It will never go to 0. And we prove that it converges towards a constant that is about 0.8 in this cavity. So this is amazing. I call this a scale-invariant cavity. You make the cavity larger and larger, the cavity cannot become multimode. The laser stays single mode. The singularity erases higher order modes. So I will give you some preliminary experiments. So, oops, I don't know why this is going fast. So here are some preliminary experiments. So the claim is that I can control the curvature of the band by basically controlling the radius of holes that form photonic crystal in this aperture. And then I truncated that photonic crystal in an hexagon, forming what I call Berkeley surface emitting laser now. So when the size of the cavity is relatively small, so D here is basically the diameter of the aperture. So when D is 19A, 9A is the size of the unit cell. This is a relatively small cavity. When the dispersion is linear or quadratic, you get single mode operation. So that's not surprising. When a cavity is small, it's not difficult to make it single mode. Okay. So the free spectral range is large when the cavity is small. So I increase the size to 27A. The cavity is still relatively small. It's still single mode. And I keep increasing the size. For 35A, when the dispersion is quadratic, the cavity starts to become multimode. And when R, the radius is larger than R Dirac, the cavity again, the dispersion is again quadratic, and the cavity becomes multimode again. But at the Dirac singularity, you tune the radius to be at the singularity. Higher order modes are erased from lasing, and the cavity becomes single mode. And the claim is that you can, in principle, increase the size forever, and this guy at R Dirac will never become multimode. Of course, provided that you implement this open Dirac potential exactly. right? Because as was just asked, if you have fabrication imperfections, that will, of course, perturb the potential, and higher order mode may come. So I didn't put all of the data here, but this paper is currently in review, and one of the reviewers was asking, oh, maybe this is not an artifact of fabrication, and this single mode operation will disappear when the size is increased. So we fabricated additional devices with larger surfaces, and this behavior is maintained. So the cavity remains single mode, regardless of the dimension of the cavity at this open Dirac singularity. The singularity basically erases the mode. So I think this is really, we can claim we actually solved the optics question of single aperture scaling. There is a way now to increase the size of the aperture and maintain single mode operation. Of course, this is just the beginning because even if I didn't explain the fabrication details, this is a suspended membrane. Of course, that's not the best configuration if you want to make a high power system later on because you have to release it, you need to pump electrically. So those are questions we are working on. So, but we have at least solved the optics question for now, and we are working on other challenges in the months, in the years to come. So this aperture can be made as large as you want. And second, multi-mode operation is forbidden. So any question? Yes, please go ahead.
So, so what kind of Fresnel number are we talking about for these cavities?
Very good. So if you take an aperture, and it's basically asking, I will show a few far field spectra because that will respond to your question. The question is mostly asking about the scaling of the far field, right? So this is also amazing because for a given aperture, since the field is occupying the entire aperture and the envelope is flat, this is the best you can do for a far field. And when you do that, the far field scale exactly as 1 over d, where d is the size of the aperture. So the far field is diffraction limited. So let me show you the next slide. So this is the far field for the apertures we made. We made larger sizes, but for this presentation, I just put those. So this little laser here emits like this. And then, of course, the far field is just the Fourier transform of the near field of the aperture. And the larger the aperture, the narrower the far field. So, and this angle, the divergence of this beam, scale exactly as 1 over d, where d is the aperture size. And this is the best you can do for far field scaling. It cannot be better than that. This is the theoretical limit, and we are at the theoretical limit because, again, the envelope is flat. In fact, what we discovered a new solution in a potential well. So if you took some physics class, the potential well are well known. All the envelopes are known. They are oscillatory. We found a solution in a potential well that is flat, a flat envelope. That has never been observed, nor predicted.
What's the round trip gain that you're?
So, okay, so the gain, so we are using indium gallium arsenide phosphide, a 3,5 semiconductor that is directly patterned. So let me just go back to maybe on this slide. So this is indium gallium arsenide phosphide, epitaxially grown on indium phosphide. And we pattern the photonic crystal directly on the indium gallium arsenide phosphide. And after the fabrication of the photonic crystal, we remove the indium phosphide to suspend the membrane. So why do we do that? So that basically the gain is the gain of indium gallium arsenide phosphide. That's what you get, multiplied by the effective field amplification in the cavity. So in the end, the effective gain is on the order of few hundred per few hundred, I would say. So around 800, that's our estimation. Because I have removed in gas P at some places, so the gain went down because it's not fully filled with gain material.
And last question. So since this is all semiconductor,
Indeed.
Have you any ideas for standard dielectric lasers, solid-state lasers, pumped, optically pumped, electric lasers. It'd be different approach. It would obviously.
So the thing is, you have to implement this potential. So the reason we have not investigated those. So we are mostly in my group interested in semiconductor laser because they are easier to pump electrically, etc. And especially if you know BerkSELs, vertical cavity surface emitting lasers, those are these days used in consumer electronics. So if you have an iPhone, for instance, they are used for face recognition, etc. So, and one of the issues with these lasers, people make arrays of them because the power can be scaled. So now we may not need to put as many BerkSELs. Of course, this is just the beginning. We need to electrically pump, etc. But we have basically solved the question that BerkSEL have had for many years. Just as a reminder, the aperture of a BerkSEL, if you want to make a BerkSEL single mode, is just few microns, maybe tens of microns. You are already much larger than that. So at this scale, a BerkSEL cannot be single mode already. So we could easily scale this power to do this type of applications or even LiDAR applications to increase the range. So that's the main motivation of the group. So to respond to your question, no, we have not looked at those other type of architectures, but the principle is universal. If you can implement these open Dirac potential, so you have to structure your dielectric because you're interested in dielectrics to implement these Dirac cones, which is definitely possible. Because it is just a photonic crystal, basically a modulation of an index in space. So if you pattern your dielectric so that the dispersion becomes linear as predicted, using symmetry protected mode, you will get exactly the same thing. So we haven't done it, but it is possible. Okay, so yes, okay, jumping around. Okay, so, and I also want to underline that this is very interesting because the far field is basically the unit cell of graphene. I find that pretty intriguing. So I form a graphene photonic crystal, form a cavity out of that graphene photonic crystal, and its far field is the unit cell of electronic graphene. Okay, so I mean it's not surprising. This is just because the unit cell has an hexagonal lattice. So in the end, so this is the superposition of the field of many hexagons that are truncated. So I will just, oops, I don't know why, sorry, it's just jumping around. I click once and it goes. Okay, so I think I have presented the first topological laser, and I've also presented the first scale-invariant surface emitting laser. So this is the first time that we have a principle that guarantees by physics the fact that the laser does not become multimode as the size is increased. So this is the first time. People have been working on this, and I will say that hundreds of millions of dollars or maybe billions have been spent on this problem. So there is a solution to the problem. Of course, there are a lot of practical questions left. So the aperture that I presented is suspended. If I want to scale power, I need to find a way to release it, and the suspended membrane is not the best way to do that. But we have not published yet, but it can be done on a substrate. We need to add electrodes to pump it electrically, etc. So those are things that we will do. Okay, so as I said here, because we solve a long-standing problem, so with my students, we decided to call it Berkeley surface emitting lasers. Not sure how reviewer will appreciate the name, but after the first round, no one seemed to complain. So that may be the name in the future. And I really think this is a new era in the area of surface emitting lasers because we can now, the race is on to increase this aperture size, find an alternative design, and make high power surface emitting lasers. And again, as I said, there is still a lot of way to go to address a few practical questions. So I will end the talk by just presenting this topological puzzle, where we want to guide light on demand. And maybe it's a new degree of freedom for kids. I should file a patent on this, and we can give it to kids so that they learn topology at an early age. And of course, I have also to thank the amazing group members who are currently with me and working on these topics. Thank you, everyone, and happy to take questions you may have. are people online.
Hi, Boubacar. Nice talk.
Thank you,
Very
Lisa.
exciting.
Thank you.
Just a simple question. What are the powers that you are measuring right
Okay,
now?
very good question. So currently we are emitting, I would say about few tenths of milliwatts, okay, with this aperture on the order of tenths of microns. And one thing that I didn't say, which also is very interesting, is I say that the laser remains single mode with the size. Regardless of the size, physics say that it cannot be multimode. And interestingly also, the laser is also robust to pump power increase. So when you increase the pump power, it doesn't become multimode until the onset of damage threshold. This is also very interesting. It's normal because the mode is occupying the entire aperture. So there is no way for higher mode to come up. So we did some estimate because this is just the first time we are making a proof of principle. But my back of the envelope calculation using efficiencies of existing diodes, if I can implement this potential on a 2-inch wafer, I can emit a kilowatt. Okay, so of course, there is a lot of issues. No, I'm working with the DoD so that we try to push the frontier. So there are lots of questions. If you put electrodes, p-n junction, etc., of course, there will be heat, right? So you need to extract the heat, etc. Those are questions we love to address. But using the efficiency of current diodes, and of course, the question you asked is a very important question. The potential needs to be implemented exactly. So you were asking about the sensitivity. So to respond even more precisely to his question, it scales. The sensitivity is exactly proportional to the wave vector, k, which is basically the effective index multiplied by the wave vector in vacuum. So meaning that, everything is in that response. The sensitivity is proportional to k. It is proportional to the effective index. So the version we made is the most sensitive because the index is suspended, so the index contrast is maximum. So when I will put it on a substrate, it will be less sensitive to fabrication. Okay? So hope that responds to your question. Yeah, absolutely.
So, with a membrane, if you're
No, it should not be a membrane as you pump electrically.
You said that at the end of the
yeah. We will do it, one thing at a time.
Yes.
Okay, but there are challenges, but I would say already the aperture that we have as single mode, you can't do that with a BerkSEL already. So this is already, even the very first version is already much better than BerkSELs.
Can you hear me? Yeah. So we have questions online. The first question was, what is the line width behavior for TIL?
Okay. So the line width. I didn't plot those data, but when you increase the pump power, the line width goes down. No, this is the well-known shallow stones behavior. So this is exactly what happened for these lasers as well. And actually, there is more work to do to try to understand fundamentally what is happening, but it seems to be more coherent than other lasers because all the aperture is in phase. So I'm observing line width that are narrower than what I get usually when I make system with quadratic dispersion. So that is not fully understood, but it does obey the shallow stone line width. And currently on the laser that we have made, the line width is smaller than a tenth of a nanometer, which is actually limited by the spectrometer we are currently using. So very narrow line width. So it could be used for communication because that's probably the question of the coherence, how far you can go while maintaining the integrity of your signal.
All right, thank you. So another question is, does lasing at just the Dirac point correspond to smaller intensities than elsewhere on the Dirac cones?
Okay, so let me go back to, that's a good question as well. So you see, this is an aperture that has a given dispersion. This is actually the dispersion of the infinite system. So the Dirac point here, this is the real part of the eigenmode. But the eigenmode also has an imaginary part, which is basically the Q factor. And we are implementing the Dirac cone using symmetry protected mode, meaning that the blue band is a B band and the purple band here are E bands. So the quality factor of this band at the gamma point, kx, ky equals to 0, is infinite in the infinite crystal. So, and in fact, what happens, I didn't go to all of these details. What happens is that the fundamental mode belongs to the blue band, is a B mode, and higher order modes are mixed, are photonic admixtures of the B band and the E band. But in the hexagonal truncation, the E mode is more lossy than the B mode. So then higher order modes are more lossy. So I keep them away from the fundamental mode. So the fact that the Q factor is large at the gamma point, kx, ky is equal to 0, this is why emission is normal to the surface. So perpendicular to the surface means kx equals ky equals 0. So if you want to laze away from the gamma point, you can take a look at actually one of our previous papers, this bound state in continuum lasers. I have a hard time with the pointer. Yeah, so in these lasers, oops, sorry. So in the bound state in the continuum laser, we have shown that we can make the IQ mode at the gamma point, and we can also put it away from the gamma point. Sorry. So the Nature paper we published in 2017, so the bound state in the continuum cavities can laze at gamma or away from gamma. And this is also interesting because we can use bound state in the continuum to do a new type of beam steering. Because it's a photonic crystal, all the unit cells have exactly the same size, yet I can emit at an angle. Usually when you want to go at an angle, you make a phase array. But this is not a phase array. They are all of the same size, yet emission can happen at an angle. So read the Nature paper and you'll have details on that. And bound state in the continuum is just a fancy name to say that you are confining light in the cavity in a special way. So maybe I can quickly explain that. If this is a cavity, the room here, so if you want to make this cavity good, what do? We put perfect mirrors on the boundaries so that the wave basically bounces back and forth and stays here, right? So now, if someone is hearing us in the hall, the door is open, the light just escapes. And then this is the way I like to explain it to my students. So light escapes, and people are hearing us. They don't want to hear us. What will you say? Close the door. To do a bound state in the continuum, you don't say close the door, you say open a second door. And what happened? Light escapes from this door, and also from the second door, but it is a wave, and they destructively interfere outside. So when you are sitting outside with two doors open, and they destructively interfere, the cavity is for you effectively closed. So the cavity is sitting in the continuum. There are propagative modes, yet at a singularity, it looks like closed. So, and we have shown that we can actually make that, use those type of things to make the cavity arbitrarily high Q. And it is also a topological singularity. We can use it to do beam steering, etc. So that's a paper we did in 2017. I don't know why the slide doesn't want to come. I will try like one. Okay, so okay. Anyway, I will. Let's take another question, and I will try to be on that slide.
Okay, so there are two questions that actually are very similar. So first question is, which applications have you mostly considered? And then there is another question, what's next for the Kanté research group? And what fields will see the biggest impact from topological lasers?
Okay, so great questions. My group, I'm really interested in downsizing the size of downsizing systems. Now, I just had a tour of NIF by Marius, and then when I was there, I said, wow, my God, I look like my lasers are like tiny compared to this facility. So we need to increase energy and information density. That's the goal of my group. So construct multifunctional systems. Again, functional is important, but that are compact in size. So for example, these lasers have been supported quite a bit by the DoD to do lasers, because if you can make power with something that is light, you can carry it everywhere. And you can put it on all types of systems. It can be useful for civilian and military applications, etc. So this is exciting to me. So I would like to make system with a small payload. Just as a story, actually, I became involved in a very crazy project that is called the Starshot, where we want to send It's not me. There is a billionaire that has so much money that he wants to send a light sail to Alpha Centauri. Okay, so and they want to propulse the light sail with lasers. Okay, and they decided to fund me somehow. So okay, why not? Let's look at some fundamental questions. And they need to communicate. They need use light for communication. So I really would like to push forward the frontier of energy density for laser. I will spend quite some time on this BerkSEL because I really think it is the most important discovery of my group to date. And I actually really think this is one of the most important papers when the paper is published in our field for the last decades, because a lot of people have been looking at this problem. And Ilya Yablunovich, my colleague, who is actually the inventor of photonic crystal, who is cited to have the Nobel Prize many times, he was really excited. He said that he tried to solve this problem. He didn't know what to do. So we will push this particular BerkSEL. We'll focus on that. And regarding the topological lasers, there is also something that I find interesting. Even that platform is more challenging technologically because you have to do bonding of some free phi with some over magnetic material, etc. So it's more complicated, even in the clean room for my students. Most students try to run away from that project. So, making a non-reciprocal laser is the key. When you make a photonic integrated circuit, a critical component is an isolator. Right? So because when energy is injected back to your cavity, it's like noise, and it kills your laser, and information is lost, etc. So people work a lot on making isolator out of laser so that you don't get power back. But in that system, what I made, in fact, I made a self-isolated laser. It doesn't need an isolator. It is already one way. So there is a lot of things to do. Lots of things to do on that platform as well. But technologically and experimentally, it is more challenging. So we have to keep thinking. So we will spend some time on lasers in the next few years. And other things. I can also say something which is just a conjecture. I have no proof of that. So these oscillatory functions that we usually see in quantum wells, in quantum physics, this is what you always see. And one of the biggest problems in quantum science is scaling. Okay, so in classical science, this is scaling. In quantum science, the only challenge is scaling. All people come up with all type of qubits from different platforms, defect, superconducting qubits, trap ions, or whatever. The only problem is scaling. So one thing this solution is telling me with the BerkSEL is that if you want a system to scale, it needs to have some loss. If the system is perfectly closed, like is the case for quantum, when you solve a Schrödinger equation, the assumption that is that everything is Hermitian and closed. So by the physics forbid scaling. So you need to add some loss, but you have to add loss the right way. That is a conjecture. I don't have a proof of this.
All right, so we'll let you think about this, and thank you for this great talk.
Okay, thank you,
and
everyone.
we'll invite you to another talk whenever you solve that question for real.
Okay, good. Okay, thank you, everyone.